You've probably seen a Slinky do its classic walk down a flight of stairs. But what if I told you that this simple, iconic toy holds a secret that seems to completely break the laws of physics? Seriously, prepare to see something that looks, well, impossible. Okay, so check this out. When you watch a Slinky drop in slow motion, something absolutely bizarre happens. The top part starts to fall, right? Totally normal. But look at the bottom. It just hangs there, in midair, completely motionless, like it's been frozen in time. So what on earth is going on here? How can one part of an object be falling while the other part is just floating? Is it actually defying gravity? Well, no. But the real answer is honestly way cooler than magic. Yeah, it's not magic, but it is all about waves. The whole secret to the Slinky's levitation trick is hidden in how information, travels through the spring itself.
Think about it like this. When the hand at the top lets go, the bottom of the Slinky has no idea that's happened yet. In physics, nothing is truly instantaneous. A message has to travel from one end to the other to say, hey, it's time to fall.
And physicists have a name for this travel. It's called wave propagation. The disturbance in this case is the release of tension at the top. That starts a compression wave that zips down the spring, coil by coil, carrying the news that the fall has started. For a regular Slinky, it takes about 0.3 of a second for that wave to get from the top to the bottom. Now, that's not a lot of time, but it's just long enough for our eyes and cameras to catch this incredible moment of what looks like pure, unadulterated levitation. But to really get what's going on, we first need to understand what makes a Slinky a Slinky. It's not like other springs, and its unique design is the real key to this whole amazing effect.
So most springs you're familiar with, like the one in a pen, are compression springs. You can squish them, you can stretch them, no problem. But a Slinky is different. It's a tension spring. See, its coils are naturally touching. It actually takes force to pull them apart, and this means you can't really compress it any further than it already is.
This graph really shows the difference. A compression spring, sure, you can stretch it or compress it, but look at the line for the tension spring. It can only be stretched. As soon as its coils touch, that's it. Game over. And believe it or not, that inability to be compressed is the whole secret to why it falls in such a weird way. Okay, so we've got our two main clues, the wave and the unique way a Slinky is built. Now, let's put them together and do a play-by-play of that mind-bending fall, moment by moment. All right, here's the breakdown. Step 1, the Slinky is just hanging there in what's called equilibrium. The tension pulling up perfectly balances gravity pulling down. Then, step 2, you'll let go. The support from the hand is gone, so the tension at the very top coil just vanishes. Step 3, that top coil, now only feeling gravity's pull, starts to fall. It falls and collides with the coil right below it, which brings us to step 4, the chain reaction. This is our wave, a cascade of collapsing coils traveling down. And finally, step 5, the amazing part. Every single coil below that wave is still in perfect balance. They're still being held up by tension, and they won't move an inch until that wave finally gets to them. You know, this isn't just a cool party trick. This effect is so fascinating that scientists have been studying it for decades. They use some pretty serious math and data to build precise models of exactly what's going on. The Slinky was actually invented way back in 1943, but it took a while for physicists to really dive into its secrets. It wasn't until 1993 that M.G. Culkin published a really important paper modeling the fall. And then, more recently, in 2012, researchers in Sydney used modern high-speed cameras to get an even more detailed picture, really nailing down our understanding. And this is where science just gets so cool. On the left, you see the real thing, and on the right, that's a computer model that simulates all the forces acting on every single coil of the spring. These models are so unbelievably accurate that they can predict the Slinky's every single move. And the data from those high-speed cameras, it proves what our eyes are telling us. This graph might look a little complex, but it's pretty simple. The blue line shows the top of the Slinky. You can see it starts falling right away. But look at the green line. That's the bottom. It is completely flat. It doesn't move at all until that dashed line, the wavefront, finally hits it. This is the hard data, the proof. The bottom of the Slinky really is stationary. So what do scientists have to plug into their equations to make these models work? Well, it's like a physics recipe. You need the Slinky's mass, its stiffness, which is called the spring constant. You need to know how that mass is distributed along its length, the force of gravity, and even things like impulse and momentum to describe the motion perfectly. So we've seen the evidence, we've walked through the physics, we've looked at the data. It's time to bring it all together for the final reveal that solves our gravity-defying mystery once and for all.
Michael Wheatland, one of the researchers at the University of Sydney, sums it up perfectly. He says there is no floating effect. The center of mass falls with acceleration g. So the Slinky as a whole isn't defying gravity at all. Its average position, its center of mass, falls just like a rock or a baseball would. The levitation is an illusion. It's a beautiful, elegant trick of motion. While the bottom of the Slinky is just waiting for the signal to start falling, the top is actually accelerating faster than gravity. Why? Because it's being pulled down by both gravity and the tension from the coils still hanging below it. This super fast collapse at the top perfectly compensates for the stationary bottom so that overall the Slinky center of mass obeys Newton's laws perfectly. The falling Slinky is just such a great reminder that there's incredible, mind-bending science all around us, hiding in even the simplest of things. It really makes you wonder, doesn't it? What other amazing secrets are just hiding in plain sight?